Thank you for the kind introduction. And hello, everybody. Good morning, Montreal people. I'm now in Japan, and now Japan is 11 p.m. But don't worry, I'm very active now. And thank you for organizers, Kroido-san and Sasada-san and Tsujimo-san. I'm very happy to talk about the box and ball system at this intensive meeting on BB. But I'm sorry for non-attendance at the meeting place. I hope to stay Canada, Montreal on Sunday. Okay, let's start my talk. My title is Viewpoints brought by the box and ball system. And I will talk about the following contents. One, family of box and ball system and its relatives. I will comment about the discovery of BBS here, and then introduce the development of things about BBS. And two.
Excuse me?
Oh, okay.
Hi, I'm very sorry. We can see in full screen.
Full screen.
Because can you reshare the screen, please?
Oh, yes, I shared.
Yeah.
すみません、辻本ですけど、スクリーンを大きくすることができますでしょうか？フルスクリーン。
Oh, excuse me. I'm now share it by full screen, but wait for a moment.
Now the screen might be smaller size.
Smaller size?
Okay, that's fine. That's fine.
Thank you.
Okay, so okay. Horizontal and vertical ratio is important. Okay, I see. Is it okay? Okay.
Yeah, it's fine.
Okay. Then I will continue my talk and wait for a moment. Second, mathematics and nonlinear system brought by BBS. And box ball system proposes discrete mathematics of piecewise linearity, and various researches have been done using that mathematics. I will show them around my research. And three, over the BBS. The box and ball system is not just BBS, and it suggests many interesting works. I will show some of them. Okay, then let's start the first section, family of box and ball system and its relatives. First, I will make an introduction about the discovery of BBS. Before BBS, there existed interesting digital near integrable systems. This is one of them, proposed by Park, Stiglitz, Thurston. The definition of the system is here. The site value is only 0 or 1. So this is cellular automaton. J is the space site number, and T is time step. SJT is a sum of state values around J at time T with a constant radius R. Here R. Okay, and every site value at next time is determined by SJT, but the dependency is interesting, and it is of filter type. The sum is constructed by the values of next time step. Next time step are here, and of the left neighbors, and current time step, sum of current time step of right neighbors. And this is an example of time evolution. Horizontal axis is space, and time is downwards. From initial data is here. Some soliton waves comes out, and they interact like solitons about here. But you can observe that some solitons coalesces here. So it is not complete soliton system. But I think this system is still very interesting because of its incompleteness. And there are other soliton cellular automata proposed by some researchers. If you hope to maintain the complete integrability, complete soliton property, the easy way is change the algebra, noting not to destroy its integrability. Here is one sample. proposed by Bruch, Santini, Ragnisco. They introduced modulo to the difference integrable equations. And some of the results I show here. And another idea to introduce some finite field is given by these papers recently. I was very interested in the Park-Stiglitz-Thurston filter type CA because I like digital mathematics very much. And then I considered how to obtain a complete soliton cellular automaton. The idea was very simple. Consider ones move in the background one-dimensional array of zeros. Then, what is the best rule to move ones? If we move ones following some evolution rule, I guess that unidirectional motion is simple than bidirectional. Okay, move ones to the right. Then, to which positions? One of the simplest rules is to the nearest right empty site, denoted by 0, in order to avoid the collision of ones each other. Through such considerations, I reached the motion rule of BBS as follows. Here, the motion rule. I raise them. 1. Prepare an infinite one-dimensional array of boxes, each of which can hold one ball at most. 2. Distribute a finite number of balls in the array as you like. We use it as initial data. Note that we can express boxes having a ball by 1 and empty box by 0. So this is a kind of cellular automaton. 3. This is the time evolution rule. Move every ball from the left to its nearest right empty box. And once the ball moves, don't move it after all other balls have moved. Okay. 4. When all balls has moved once, increase the time step by 1 and return to the step 3. Please note that if we change the space direction, left to right or right to left of the above rule, then we obtain the reverse evolution. So this is a reversible system, and the reversibility is welcome as an integrable system. Here I show 2 examples of time evolution of BBS. The right figure shows the interaction of 2 solitons. The left soliton of length 3 moves at speed 3, and it passed the right soliton of length 1 of speed 1, and showing the phase shift of both solitons. And the same solitons again appear after the interaction. Okay. And the below one shows interactions among 4 solitons of length 4, 3, 2, 1. The interaction is simultaneous for more than 2 solitons. But soliton profile preserves before and after the interaction. We can analyze, we can always obtain pure soliton interaction from any initial data, calculating backward or forward evolutions. And BBS, this system, is apparently a pure soliton system. If you try some cases, then you can believe immediately this system is a complete soliton system. We obtain the following question naturally. Where does this system come from? What is the relationship with conventional soliton system? And the answer came 5 years later. If we don't have the final answer, we can analyze the mathematical properties of BBS closed in this game. If the system is soliton system, then we should discuss about initial value problem and infinite number of conserved quantities. And about the initial value problem, there are few methods to identify the position of solitons and length of solitons from an arbitrary state. Here shown is one method, but I omit its details. And moreover, strongly relating to the identification of solitons, there are an infinite number of conserved quantities calculated from any state in the evolution, and which are expressed by the number of pairs of one ball and one empty box pair of depth k. This expression of conserved quantities is connected directly to Dick-Lange and Young tableau in the mathematical field of combinatorics. It was a lucky thing that definition of BBS using boxes and balls is highly extendable. Consider the situations that the capacity of boxes is larger, or the balls are numbered, then both extensions preserve integrability. For example, this is an evolution equation of a box and ball system, and this constant one was first strange, but afterwards we know that it means the capacity of boxes. So if we change this constant by 2 or more integers, then this evolution equation gives the BBS with larger capacity. This left figure is an example of boxes which can hold 3 balls at most, and soliton profile occurs. Okay, these numbers means the number of balls in every box. Okay, and the right figure is an example of BBS of numbered balls. Every ball has a number, and we move them not from the left, but ball with smaller number earlier. Okay, so about this state, we move first the ball numbered 1 to here, and then number 2 ball here, number 3 ball here, and so on. Okay, and the mixture of these two extensions, that is BBS of larger boxes and numbered balls, is still soliton system. And the capacities of boxes can be changed depending on site position, but integrability is preserved. Next, we obtained the important clue to derive the BBS from the non-soliton equations. BBS is first order. Please look at this table. BBS is the first order on time, and the direction of soliton propagation is unidirectional. Okay, and we already knew that Korteweg-Dofris equation, soliton equation, differential equation, is first order and unidirectional. And we have toda lattice equation. That equation is second order and bidirectional. So about the BBS, we can extend it to second order and bidirectional, I guessed. And please look at this right part. This is toda lattice equation. And if you change toda lattice equation of second order on time and space only by changing the differential and the difference operators by first order here, then you obtain the equivalence to Lotka-Volterra equation, which reduces to KdV by continuum limit. In parallel with that, if you transform the variable UJT to VJT through these transformations, then you obtain first order difference equation on time and on space of BBS. So comparing these two equations, this equation and this equation, we can guess that max 1x corresponds to exponential x. So if we change the left equation to second order, then we may obtain Toda-like BBS equation. Okay. Obtained the second order soliton cellular automaton.
Excuse me?
Okay.
There is a question in chat.
Oh,
Professor
chat. Okay.
Yes, may I ask just a
Wait
very
for a
quick
moment.
question?
Okay. I can see a chat anytime, but
Yeah.
no.
No,
question.
it's not in chat. He's with his mic.
May I?
You can go ahead.
Ask a quick question?
Okay.
You're using the word integrability. Could you please define it?
Oh, so it is a little difficult, but in my talk, it is very easy definition. So the existence of n solitons, or existence of an infinite number of conserved quantities.
So you do not require something like a linear lax pair.
Yes. Yes, we can consider those things afterwards. But now I recall the history of BBS. So at this stage, that thing have not come. Okay.
So the definition that when you say that it preserves integrability when you make these changes, the definition is an infinite number of conserved quantities.
I'm sorry.
When you say that you go from, let's say, a single particle to 2 or 3 or occupations, you say you want to preserve the integrability. So do you mean by that you want to preserve the property that there's an infinite number of conserved quantities?
Yes. So, okay. So when I found the box and ball system, it has an infinite number of conserved quantity exist. We proved, but the proof is very manual procedure, like the solution of a chess game, not the lax pair. Is this your answer?
Well, you answered as far as definition is concerned, but I don't know how you would actually, in practice, if you don't have a lax pair, I don't know in practice how you could prove that there are an infinite number of conserved quantities.
Okay. Please let me consider the answer. Afterwards, I will answer, or someone will answer your question. May I continue my talk?
Yes, thank you very much.
Okay. Okay. Thus, here, Toda CA obtained by minimum. Okay. Thus, we obtain the second order soliton cellular automaton, which is now admitted as an ultra-discrete Toda lattice equation. At that time, we have not yet been confident that max operation is a key function, so we made it with minimum definition. Here, the function is very minimum definition. But the form is very beautiful about the symmetry on space and time. Here I show 3 cases of soliton interaction. The first is 2 solitons of the same propagating direction. The second is of opposite directions. And the third is interaction among 4 solitons. The dots means 0, number 0, integer 0. Okay. Then 2 evidences have been obtained at that time. One is of first order, and the other is second order. And comparing and observing these systems, Tokiro-san and Matsugira-san found the pathway from different soliton equations to soliton cellular automata. The key formula is this. It is very simple limit formula, and if we apply it to the difference Toda, this equation, difference Toda equation, and difference Lotka-Volterra equation, this equation, they are integrable. And then taking the use the transformation variables and take the limit, then we obtain ultra-discrete Toda equation and ultra-discrete Rotka-Volterra equation, which is equivalent to box and ball system, as I shown before. This stage, we finally got the full scenario about continuous and discrete equations from the viewpoint of integrability. Here, I show the full scenario about KDV. The difference equation is most principal here. Difference Rotka-Volterra equation here. And if we take some continuum limit, then we obtain differential analog, this KDV equation. And if we apply some ultra-discrete limit using this transformation variable and parameters, and epsilon take to +0, then we obtain this ultra-discrete equation. And this equation is piecewise linear, and its operations are constructed from max, plus, and minus. Moreover, if we can set the coefficients, parameters, and initial data of this equation to be integer values, then it becomes integer-valued evolution equation. That is cellular automaton in a wide sense. And moreover, if we are lucky to have an appropriate transformation, then the state value of cellular automaton can be closed in a finite set, for example, 0 and 1. And this is BBS, box and ball system. Okay. And once we know the pathway from difference to ultra-discrete, many variations can be produced. I show the examples only about BBS in this page and the next page. This is BBS with a carrier of balls. And this system is derived by ultra-discretizing the difference modified KDV equation here. And ultra-discrete version is here. And this system is very important in the mathematical sense because the change of number of balls in the box and in the carrier before and after passing each box can be interpreted as the operation of combinatorial R. So this system has very important meaning. Okay, and here I show 4 examples of BBS. This is made from the quantum affine algebra using crystal base, which is almost equivalent to ultra-discretization, and much more variations of BBS can be produced from this context. Okay, and this is box basketball system using basket which play a similar role of box. And this system is not a new BBS, but is analyzed from the viewpoint of randomness. And I think details will be explained by Sasada-san and Tsujimoto-san, maybe on Wednesday. And this system is proposed by also Tsujimoto-san. It is defined by a state transition diagram here. And that diagram can produce many kinds of BBS, and it is still strange for me because many rules cannot be expressed by an ultra-discrete evolution equation. So this is a very question for me still now. And next, I will talk about 27. Okay. Next, I will talk about mathematics and nonlinear systems brought by BBS. There are 2 main players about mathematics. One is ultra-discretization. The other is max plus semiring or max plus algebra. And this semiring is also called mean plus semiring or tropical semiring. About the former one, I show here the 4 basic patterns of ultra-discretization process. I already introduced this plus sign formula I shown before. And about minus, it is not well defined in the range of real value. And about multiplication and division, they are very easy formulas. And the left-hand side becomes this A plus B and A minus B. Thus, the algebra proposed by ultradiscretization is semi-ring with addition max and multiplication plus and division minus. Okay. And here is a typical, here is a typical example of mapping. If we use transformation of variables and take this limit, then we obtain a mapping on capital Xn from that on small xn. Please note that we can omit this transformation and limit if we only replace operations addition by max and division by minus, and this constant one by 0, then we automatically obtain this max plus equation. So ultradiscretization is a limit process in one sense, but in another sense, it is change of algebra. And about max plus semi-ring, unfortunately, subtraction is not well defined. But if all things are automatically transformed, it is not so interesting because it is automatic. The fact that the subtraction is not well defined makes the max plus game more interesting. To solve the subtraction problem in the ultradiscretizing procedure is called negative sign problem. I will comment about it afterwards. And about soliton integrable system.
Excuse me?
Yeah.
Professor Hollner has a question. If you
Okay,
want to
sorry, another quick question. It's just a question of definition. Is there a theorem that says that if you take an integrable system like KdV or Toda and you ultra discretize, that discrete system itself is still integrable?
Yes, but it is difficult to the equivalence of integrability because ultradiscretization is a limit process, and so some fine profiles will be lost. It is related to your previous question. So what is integrability? But many algebraic properties are preserved. So we believe that the ultradiscrete system made from the different soliton equations, which are if they are integrable, then ultradiscrete systems are still also integrable.
I'm just asking if that's a theorem or just a conjecture.
Yes. Okay. Maybe I can't answer exactly. So afterwards, please, my collaborators, please answer his very deep questions. Okay. I'm sorry. I can't. I don't have the exact answer for your question. It needs a very exact definition of integrability, and I have not considered about it. So n-soliton solutions exist, and infinite number of conserved quantity exists, then I admit that system is integrable.
It remains a question whether it's a theorem. So even if you take that as a definition, does it follow that if you take a continuous integrable soliton system and ultra discretize it, that the resulting discrete system both admits solitons and an infinite number of conserved quantities? Is that a theorem or a conjecture?
No, because we only obtain the ultradiscrete system using by transformation of variables and limit. So if that limit breaks the integrability, then it is not integrable. But the limit is very simple. So the integrability is preserved, I think. Okay, then I will okay. Then next page. From now, I will show you some examples about nonlinear systems related to ultradiscretization or max plus semi-ring. And let us assume the situation that we want to make cellular automaton from differential equation, or make differential equation from cellular automaton, which must be analog each other in some sense. Then we usually follow this schematic algorithm: differential, difference, ultra-discrete, or max plus, and cellular automaton. If you start from difference equation, then almost things go smoothly because we can obey the almost unique procedure. Almost this direction are all almost unique. So it is not so difficult. But if you follow these relations in the reverse direction, so from down to top, okay, there are some problems about them. And first case, from differential to CA, when we want to make CA from differential equation and discuss about their relation, first we should make some difference equation from differential equation. But there are many candidates about difference equation corresponding to the original differential equation. Maybe you know it well by the finite difference methods to calculate differential equation numerically. Okay. And moreover, you must ultra-discretize the obtained difference equation. But if negative sign exists in the difference equation, ultra-discretization of that part is not well defined. So we can't ultra-discretize. From CA to differential equation, when you want to make differential equation from a cellular automaton and discuss about their relation, first we should make max plus equation which can include the original CA as a special case. Because max plus equation is integer valued equation, and cellular automaton, the value is closed in a finite set. But there are many candidates about max plus equation because there is vast freedom about upgrading the binary operation to the max plus operation. Moreover, after obtaining max plus equation, we should make some difference equation by back ultra-discretization of max plus equation. But it is backward process of limit. So there are large freedom about the difference equation. Of course, if you follow this algorithm very formally, it is not so difficult after some experiences. But the behavior of solutions or algebraic property of the obtained system is often very different from the original system. So formal translation is almost nonsense. But I'd like to emphasize, solving these problems need a certain level of professional technique. So it is very interesting. We must find a valid relationship in some sense among many candidates of equations of different level of discreteness. And in some cases, the correct answer is not unique. It depends on what we hope to obtain. Okay. When we want to obtain the ultra-discrete system analogous to some differential model, we often meet the negative sign problem. To avoid this, we must make the difference equation without negative sign, and simultaneously, it must be some approximation of the original differential equation. Okay, so it is very difficult problem. And Ralph Willockson and his collaborators succeeded to ultra-discretize SIR model, known as a famous epidemic model. They made very nice difference SIR analog by using Taylor expansion of 1 over 1 plus x. 1 over 1 plus x can be expanded 1 minus x plus and so on. So the minus sign here is embedded in the operation 1 over 1 plus x, and division and plus is in the max plus semi-ring. Next example is about the famous differential model known as traffic flow model called optimal velocity model. I and Matsukiara-san derived the difference equation, which approximates the original differential equation. Please look at these two blue-lined terms. About the first one, the original term is only v, but we use log 1 plus delta square v in the difference equation, and delta is an interval of time steps. And about the second term, the original term is only the derivative of xk on time, but we use log 1 plus delta exponential something here. And these devices lead to success of ultradiscretization and the occurrence of traffic. This is the ultradiscrete version. And the occurrence of traffic jam can be reproduced in the max plus equation. Okay. And next example, I must comment about it. Next example is again about traffic flow model, but another type. This is an example from CA2 differential equation. Okay. And please assume that we have only this cell automaton. We have only this cell automaton and don't know these things. Okay. And that's okay. This is famous cellular automaton called elementary cellular automaton of rule number 184, and it is used as a basic traffic congestion model. Like box and ball system, ones move to the right in the array of background zeros, shown in these figures. And it is interesting that this CA shows critical behavior at a critical value, 1/2 of density of ones. Ones are moving like particles. We can express this rule table by max plus equation in the conservative form, because this is a conservative system, so we can write the equation in the conservative form here, ultra-discrete conservative form, okay, with a conserved quantity of the number of ones. And moreover, it can be linearized using this transformation variable. Then, okay, and we have this system. This is a linear equation in the ultra-discrete world because max is addition. Okay, and then they can be back ultra-discretized and obtain this system of difference equation. And then we can make a continuum limit from this to this. And this is the Vargas equation and diffusion equation through Kohl-Hopf transformation. And moreover, using this ultra-discrete diffusion equation on F, we can prove the initial value problem about these phenomena and can explain the critical behavior of solutions even for the real valued initial data. Okay, so 0-1 game changes to the equation. Okay, and I omit something. This is the example about chaos. Kajiwara-san and his collaborators succeeded to ultra-discretize the solvable chaos. Okay, I omit, skip. And this is my results. And this is about dynamical system with limit cycle. And the differential and difference and ultra-discrete, we obtained a very beautiful triplet. Okay, and I omit it. And the last section. Okay, the title of the last part is Over the PBS. Explained so far about things related to ultra-discretization and max plus semi-ring, but obtaining much experiences about these things I became more interested in the mathematics and non-real systems described only by max operations, putting aside the difference and the differential system. Okay. From this point of view, I noticed that elementary CAs can be upgraded and be embedded in max equations. Here I show the definition of elementary CA, which can be defined by this binary rule table. And Wolfram analyzed the 256 ECA rules from the viewpoint of statistical mechanics and shows that they can be classified into 4 classes about the asymptotic behavior. The state goes to the uniform state in the class 1 ECAs, and traveling wave pattern class 2, and triangular pattern class 3, and more complex case. I and my collaborators tried the similar things for the cellular automaton, and we can embed any cellular automaton in the difference equation described by the lattice operation, shown here. The word of lattice is the same as that of the Boolean lattice, and it proposes the diverse mathematical objects. And here I translate them by replacing or by max and by mean, and conjugation or negation by minus. Let's consider an arbitrary evolution equation using lattice operations, that is using max, mean, minus. Here is one example. Uj n plus 1, n is the time, j is the space, equal max, mean, etc. Okay, then we can solve this equation and arrange the terms, and we obtain the solution, very nice solution here. Okay, and if we set the values 0 or 1, then it becomes the elementary cellular automaton of rule number 232. And this is the binary, this becomes a binary solution. Okay. So these figures are the solution, and this is a solution to ECA 232. And this is the solution of expressed by this solution. And this is real value. And please note that this solution is only a special case of this very general real valued solution. Okay, so we can embed the ECA, cellular automaton to the lattice equation. Then, if we have the encyclopedia about lattice equations and their solutions, we can know mathematical structure of binary systems much more, because they are embedded in the lattice world. Our mathematician will do such things usually we do such things. Real valued function we understand embedded in the complex function, or low dimensional differential equation embedded in a higher dimensional differential equation. Okay, so I think such embedding is very important. And, this is one example. This is binary system ECA8, and these are binary operations, negation and AND. And this is a max equation, mean minus. We're using mean minus, and solving this binary system from any initial data, after 2 time step, the solution becomes uniformly 0. Okay, but if we solve this equation, we have this general solution using the initial data, and it is a little complicated. The value ujn depends on from j-1 to j plus n of initial data. So the pattern becomes a little complicated. And this very simple profile is embedded in this real valued solution. And time comes. Yes. Okay. Okay. This is an example of game of life. So I will conclude here. Okay. I talked about many things, so I can't give a compact summary, but at least I can say BBS brought us quite new viewpoints for both discrete and continuous systems. And here I show the full story from differential KdV equation to BBS. And the right example is about pattern formation system using very simple max plus equation here. Okay, looking at this, I'd like to send you this statement. Continuous or discrete, it does not matter.
Thank you, Takahashi sensei.
Okay.
And okay, so if you have any question or comment, please. Okay, so Okado sensei, please.
拍手だったんですけど
Oh, 拍手、oh, sorry.
遅かったですよ。
Okay, so Takahashi sensei, the last part you omit many things. So if you have so please explain short time, very short time.
Okay. Okay, thank you. Thank you.
Yes.
It is most I want to say.
Yeah. Especially the game of life is very interesting. I think.
Yes, yes, yes. Okay. The Conway's game of life, maybe all of you know about it. And this is two-dimensional binary game. And there are many exact solutions as moving patterns or static patterns here.
Mm-hmm.
And recently, Lafla proposed a smooth version of smooth life. It is a continuous game of life, continuous version of game of life. And I omit the definition, but the solution is very curious.
Mm-hmm.
And looking at this, at once I noticed that it can be expressed by max plus equation and changing the function by the max plus operations. And this is the max plus version. And the evolution equation is very simple. Uij n plus ij is a two-dimensional space variable, and n is a time. And uij n plus equal function s of m and n. And s I replaced from the original one, from original smooth life. And this s can be expressed by only by max and plus and minus. Okay. And m and n are average value of inner domain and outer domain. Okay, so this is very simple. And if radius is appropriate large, then we have the similar solution. But it is not the most interesting thing. If we set the radiuses to the very small, then we have this max plus equation.
Mm-hmm.
And this max plus equation is if we set the all values at 0 or 1, then it is equivalent to the game of life. But the game of life is a binary game. But max plus equation is basically the real valued solution it proposes. And about the exact solution to this max plus equation, we have these kind of solutions, and including a free parameter A. And looking at this example, this is oscillating solution. This is exact solution. And if we set A equal 1, then we obtain the binary solution, and it was reported in the game of life, the pattern of clock. And if we set A equals 0, then toad occurs. Okay, so this means that we can unify the binary patterns of game of life in one solution, real valued solution. And please give me a little more time. And
Okay.
we have to do the same things. And I can't do this by myself. So young people of my laboratory did this. And they reported very many such solutions, unifying solutions. And then more very surprising thing occurred. All these solutions can be unified in one solution. Okay, this is the previous Max Plus equation. And assume oscillating pattern and assume some symmetry on space. And if these variable u are defined by these system of parameters, there are 20 parameters, then this equation is exact solution of this equation. And if something set to be 1 and others are 0, because this condition necessary, then the binary pattern again obtained. So all of these patterns are unified in one solution. And I think this is a very, this proposes a very important meaning, because the game of life is basically only the simulation game. But using this procedure, upgrading the binary game to the Max Plus equation, we can solve as some evolution equation. I think this is very important. Okay, this is what I want to say.
Thank you so much. Yes. Thank you. Yes. Okay. So, is there any question or comment? If not, I will get at the close here. Thank you, Takahashi Sensei.
Thank you very much. See you. Okay. I will.